So I hope you guys have understood the basic way in which you have to draw the shear force diagram, bending moment diagram. So we'll be going ahead with the next example, that is cantilever beam with uniformly distributed load. So put the heading and you can go ahead with the first step. So cantilever beam with UDL. So this is a cantilever beam having a length L and the intensity is there, which is having intensity of uniformly distributed load is there, which is having intensity of Q Newton per meter. So if you take the free body diagram, you will be having this uniformly distributed load over this length L. So we have this reaction force Rx, Ry and M0 since it is a fixed support. So please let me know the values of Rx, Ry and M0. Come on, do it. Very good. So actually while dealing with this, what you should do is you should do one extra step, that is you should take an equivalent load. So this Q is a uniformly distributed load acting like this. So it is nothing but a point load of magnitude Q into L acting at a distance of L by 2 from both the sides. So we are taking this equivalent load here. It becomes easy to deal with this. So how we should take equivalent load? So the magnitude of equivalent load is area of this shaded region. So it is intensity is Q, length is equal to L, and it should be acting, or the load should be passing through centroid of this area. So this is nothing but L by 2 from left side. So here if you take this, we should take Rx, will be having Ry and the reaction moment M0. So if you do the calculation, you will get Rx as 0, Ry value is equal to nothing but Q into L, and M0 value will come out to be QL square by 2. So these three values will be getting by application of equilibrium condition. Everybody got these values? If you are unable to deal with this, now you take this diagram, you solve it and get these values. Please don't skip any step thinking that it's going to be very easy. For every question, whether it is silly question, easy question or very good question, I want you people to do each and every step. Okay, kindly do that step. Everybody let me know once you get the answer. I hope everybody have copied this. So we have calculated that so uniformly distributed load of intensity Q Newton per meter is there. Rx is 0, Ry is Q into L, and reaction moment is QL square by 2. Okay, and this length is equal to L. Now here, if you take a cut, obviously we should take a cut over a distance x from the left side to draw the shear force diagram or bending moment diagram. So origin is at the left end and we are taking x at the cut. Now if you take the left part of the cut will be like this. So this is having a uniformly distributed load of intensity Q over a distance x, and here there is Q into L, and reaction moment QL square by 2 is there. Okay, and according to our sign convention, we should take shear force V upside and bending moment M anti-clockwise. So for this, apply the equilibrium condition and get the value of shear force and bending moment. Come on, do it everyone. Get the function of shear force and bending moment. What are the values? No? Okay, look here. So again, as we have this uniformly distributed load, we should take the equivalent load. So Q is acting over a distance x. So this becomes Q into x. This distance is x here. So we have QL square by 2. So here we have the point load QL. So we have shear force and bending moment like this. Shear force V and bending moment M anti-clockwise. So if you apply the equilibrium condition, sigma Fy is equal to 0. This comes out to be QL plus V minus Qx is equal to 0. So V comes out to be Q of x minus L. Now sigma Mz is equal to 0. So take moment about this point, M anti-clockwise, Q into L into x clockwise. So minus QL x, Qx into x by 2 anti-clockwise. So plus Qh square by 2 anti-clockwise and QL square by 2 again anti-clockwise. So plus QL square by 2 anti-clockwise is equal to 0. This gives us the value of M as QLx minus Qh square by 2 minus QL square by 2. This is the value of bending moment equation. Understand? So M anti-clockwise, QL into X clockwise, QX square by 2 anti-clockwise, QL square by 2 anti-clockwise. So if you draw the shear force diagram, so it's very obvious that X power 1 is there. So this is going to be a straight line. Okay. So to draw a straight line, we require 2 points. So at X is equal to 0, we understand it is nothing but minus Q into L. At X is equal to L, it is nothing but 0. So this is going to be a straight line. Understand? And if you draw this bending moment diagram, so here it is X power 2. It's going to be parabola. So to draw a parabola, we require more than 2 points. So you should actually go like this. Like at X is equal to 0, what is the value of bending moment? At X is equal to L by 2, what is the value of bending moment? X is equal to L by 3, what is the value of bending moment? Like that, you should take some couple of points and you should draw. So I'm skipping those lengthy calculation. So if you plot and draw that, you will be getting the curve like this. At X is equal to 0 is nothing but minus QL square by 2. So minus QL square by 2. And it goes on like this. At X is equal to L, it's going to be 0. So QL square, so minus QL square, it becomes 0 here. So from these two diagrams, you can say V max magnitude is nothing but Q into L, and M max magnitude will come out to be QL square by 2. So V max magnitude is Q into L, and M max magnitude is QL square by 2. So that is the way in which we have to draw the shear force diagram, bending moment diagram. So I hope it is. I'm hoping that whatever the bending moment equation you got is correct. Kindly check if it is wrong. So anyway, if I did any calculation mistake, you can also let me know, because we are doing mathematical calculations. There is definitely a chance that sometimes we do mistakes. Okay. So this is how we draw it for this loading case. Now we'll be going with the third loading condition. Everybody done with this? Copying is over. Shall I go ahead with the third example? So third one is cantilever beam with triangular load. So triangular load in the sense, and going with that condition where maximum intensity is on the left side or the fixed support, that is Q Newton per meter. Okay, and zero intensity is in the rightmost corner. May I know the values of reaction forces and reaction moments here? Can you guys try? Based upon the concepts or explanation I given in the previous example. I would like to know the values of Rx, Rv and M naughts. So here again we should draw the equivalent diagram. In fact, we should take equivalent force for this triangular load. So we have this Rx, we have this Ry, and we have this M naught. So total magnitude of force due to this Q is area of this triangle. It is nothing but half Q into L. And for a triangle, you know, the centroid location will be L by 3 from the left side. For right triangle, you know it is L by 3. So this will be acting at a distance of L by 3 from left side. So for this, may I know the values of Rx, Ry, M naught? Okay. So Rx value will come out to be 0. Ry value will come out to be half Q into L. And M naught value will come out to be Q L square by 6. So these are the reaction forces and reaction moments for this beam. Kindly copy till here. Once you are done copying, please let me know. I'll drop that and go ahead with the next step. So if you take this beam, it is like this. This triangle load is there. Q Newton per meter. Rx is 0. Ry is nothing but QL by 2. And reaction moment came out to be QL square by 6. Okay. So to draw the bending moment diagram, same way we should take a cut at a distance of x. So x-axis is like this. This is origin. Now if you see the diagram, left side of the cut is like this. So here the intensity is equal to Q Newton per meter. Reaction force is QL by 2. Reaction moment is QL square by 6. And this distance is x. It is like this. So this distance is obviously nothing but L minus x. Now if you are taking shear forces, it is like this: V upside, this is V downside. M anti-clockwise should be taken here, and M clockwise should be taken when you are dealing with the right side of the cut. So when you see these two diagrams, left side of the cut and right side of the cut, which one do you think will give us the answer easily with lesser calculations? Left part of the cut or right part of the cut? Which one will give us the answer easily? What do you think? Obviously it is right side part, because we don't need to deal with this type of trapezoidal type of load or varying type of load. So here it becomes completely a triangular type of load itself. Okay. So but here one problem is, we should know the value of this intensity. We should know this amount of intensity here. This is not equal to small q. Let's take this intensity as capital Q. We should get the value of capital Q. So how to get this capital Q? Look here. Along the x-axis, intensity is varying like this. At x is equal to 0, intensity is equal to capital Q. At x is equal to L, intensity is equal to 0. At some distance x, intensity is equal to capital Q. So if you take these 3 points, they are lying on a straight line. So slope between AB is nothing but slope between BC, or you can take it as AC. So AB slope is nothing but capital Q minus small q by x minus 0. So AC slope is nothing but 0 minus q by L minus 0. This gives us capital Q is equal to Q into 1 minus x by L. This gives us capital Q into L minus x by L. So capital Q is equal to Q into L minus x by L. Okay. So I hope there is no confusion regarding how to get this capital Q. Now we got this capital Q. Now you can do the remaining calculation. You can do on your own as well, simultaneously with me, and you can cross check the final answer. So I'm taking the right side part of the cut and doing the calculation. So it is nothing but or equivalent to half capital Q into L minus x, which is acting over a distance of L minus x by 3. So here V should be taken downside and M should be taken clockwise, and this is the point here. And capital Q is equal to Q into L minus x by L. So here if you take sigma Fy is equal to 0, this gives you minus V minus half capital Q into L minus x is equal to 0. So V comes out to be minus half capital Q into L minus x. So V comes out to be minus half into capital Q is Q into L minus x by L into L minus x. So V is equal to minus Q by 2L into L minus x whole square. This is the shear force diagram equation. In the same way, if you apply sigma mz is equal to 0, so we can say that m clockwise, that is minus m, half capital Q into L minus x into L minus x by 3 clockwise is equal to 0. So this gives you m is equal to 1 by 6 into L minus x whole square, 1 by 6 L minus x whole square into capital Q. Capital Q is equal to given as this one here. So small q into L minus x by L. So m is equal to q by 6L into L. We are having a negative sign with this. Negative sign is there. L minus x whole cube. Q by 6L into L minus x whole cube. So this is the equation for M. So we are getting when you want the equation as a cubic equation, and we are getting shear force diagram equation as a quadratic equation. So it's a parabola and it's a cubic equation. Okay. Kindly copy till here. I will rub the board and I will draw the shear force diagram and bending moment diagram here. As they are not straight lines, we need more than 1 point. Then only we will be able to get the value of shear force and bending moment diagrams. So if you plot the diagrams, you will be getting the answer like this. Shear force diagram equation will come like this. X, this is 0, this is L. So shear force diagram equation will come out to be like this. At x is equal to 0, you will be having this value as minus QL square by 2. And x is equal to L, it's going to be 0. In the same way, if you draw a bending moment diagram, M, this is x, this is 0. So at x is equal to 0, the bending moment value is equal to minus QL square by 6. And x is equal to L, it is equal to 0. So you'll get this like this. Understand? And if you get the value, Vmax magnitude comes out to be QL square by 6. And if you see the magnitude of M max, it comes out to be, sorry, it is QL square by 2. Sorry, QL by 2 will come, sorry. Because it's a moment, it's a force here, QL by 2 will come. And this will comes out to be QL square by 6. So kindly copy till here. We'll go with the next 3. So copying is over. Shall we go ahead with the next one? So we see that only little mathematical calculations are extra there. So all at the end we are doing, or we are applying the conditions. We are applying these equilibrium conditions. That's all. Chandresh, actually we have to remember Vmax and Mmax. It's better. Okay, but not for every loading condition, because few things will automatically get remembered. Okay, but for few cases we have to remember. I will tell where mandatory you have to remember based upon the previous gate questions. Not for this, not that much required. In fact, we'll understand few shortcuts in the coming concepts. So shortcuts will help you to relieve your burden in terms of mugging, instead of mugging up this. Okay. If you are forgetting also, on the spot you can do the calculation very fast and get the answer. Okay. So because no gate question came on this type of loading where calculation is a little bit lengthy. But as you are doing the calculation for the first time, you will feel little very difficult. But when you are doing for the, like when you are doing practice and then you are doing, then you will not take this amount of time. Okay. Let's go with the next one. So next one is cantilever beam with point load in the middle. Cantilever beam with point load in the middle. Okay. So this is a cantilever beam having length L. So this W is L by 2 from left side and right side. Okay. If you do the first step, it's easy only. You all can do it. So you'll get Ry as W, Rx as 0, and you'll get this M0 as WL by 2, and this is equal to L by 2. This is equal to L by 2. Okay, so you'll be getting those reaction force and moments. Kindly copy till here and listen to my statement carefully, or listen to whatever I'll explain very carefully, because we'll be doing on a very important extra step in these type of numericals. Once copying is over, please let me know. Okay, look here everybody, carefully look here everyone. Till now, whatever example we took, we have taken only one cut. For the whole length of the beam, we did only one cutting. But whenever, listen to my statement carefully everyone, whenever you have point loads or point moments in between the ends of the beam, obviously if you have a simply supported beam, you'll be having point load at the corners. Okay, I'm not talking about them. So if you have point loads or point moments in between the supports along the length of the beam, in between the ends along the length of the beam, then we always should cut the beam before and after the application of point load. So here the point load is acting here. We should do the cutting twice. Okay, this point load is coming between the ends. So you should be cutting before this W, and you should be cutting after W also. So we should be doing these multiple cuts. So this is first cut. I'm doing this first cut just before W, and second cut is just after W. For example, you take length is equal to 1 meter. This is x-axis, length is equal to 1 meter. So total length is equal to 1 meter means W is acting at 0.5. So first cut is made just before 0.5, something like 0.4999 like that. Understand? Second cut is made just after 0.5. So 0.4, 0.5, 0.1111 like that, something like that. Okay, after 0.5. So after 0.5, second cut. Before 0.5, first cut. Clear? Any doubts? I'm writing the statement. You can copy. Kindly write down clearly. This step is very crucial whenever you see. This step is very crucial whenever you see this a point load is there or point moment is there in between the ends of the beam. Okay. So you guys understood that for this example we have to do multiple cuts. One cut before the application of load and one cut after the application of load or after the location of the load. Okay, everyone, look here. Everyone, look here. Please pay attention. So we generally take each and every part before the cut. So if you take the first cut, we are taking this left part of the cut, and we are taking this x-axis like this. So when you take the left part of the first cut, it is like this. This distance is x. It is having a point load W. So here there is W L by 2. So this thing is there. Now we have to take shear force upside and we should take bending moment in anti-clockwise sense. So for this one, range of x is including 0 and not including L by 2. Everybody got the clarity of this range? I kept equality sign for 0, that means 0 is included, but no equality sign for L by 2, that means L by 2 is not included there. You're able to understand? Any doubt regarding this thing? Because I took this part. This is varying from, for example, you take L by 2 is equal to 0.5. It is up to just before 0.5, right? So L by 2 or 0.5 should not be included. But 0 is included. That's why I kept that range. Any doubts? Clear? So for this you can derive the value of V and M. So you can easily get, so V is nothing but, so V plus W is equal to 0. So V comes out to be minus W. If you want to get the value of M, you should take moment about this point. So M anti-clockwise plus WL by 2 anti-clockwise minus W into X is equal to 0. So M comes out to be Wx minus WL by 2. So this is the expression for, equation for V and M. I hope there is no doubt. Okay? So I hope everybody have copied. Now look here. We are done with taking left part of the first cut. So we took this part here. Now what we should do? We should actually take this part, left part of second cut till right of first part, or right of first cut. Am I right? For this one, what is the range? How can you write down the range for this one here? This is including 0.5 or L by 2 here. It is starting by including L by 2 but not including L. It's not including L. So for this one, the range will come. So if you take that, the range will come as X including L by 2 and not including L. So this is the range for that. Am I right or not? You understood how to write down the range here? Okay. So strictly speaking, what we should do is, we should take right part of the first cut till left part of the second cut. So we are interested in finding out shear force and bending moment at second cut. So shear force should be taken as V upside. Okay. And bending moment should be taken anti-clockwise M. And this is the point about which we would like to get the value of moment. Clear? Now everybody listen carefully here. Everybody listen carefully here. You just have to be a little bit patient or have to listen carefully. So strictly speaking, we should take this part, that is this diagram, and we should get the, or we should apply the equilibrium condition to get the answer. So this is nothing but the right part of the first cut. So whatever V and M you got, we should use the same values. So here we just now derived that V is minus W. So here we are taking V upside, means here we should take V downside, which is nothing but minus W. Okay, and here M is equal to anti-clockwise, means you should take it as clockwise moment. So M is equal to given as Wx minus WL by 2. Right? Understand? Okay. So here we have taken X. So here it's going with X only. X itself. Now look here. It is little bit difficult and complicated to deal with this one. Okay, because we should take these V and M which are functions of X. It becomes difficult for us. Sometimes you can have confusion. So here we can reduce our efforts, because at the end our objective is to get the value of V and M at this location. All I am concerned is to take the second cut, because I want to get shear force and bending moment at the second cut. So there is no compulsion that I should take the first cut, because at the end I have to take the second cut. Second cut should be there. Shear force V and M at second cut should be there in the diagram, and we should apply the equilibrium condition. Whether I apply equilibrium condition for this part of the beam or for the whole part of the left part of the beam, I'll get the same answer. So at the end I'm applying equilibrium condition. So what I can do is, instead of taking this part, I will take the whole diagram till the left part here. So instead of doing this, what I will take is, I will take the whole diagram till the left of the second cut. So here there is distance given as X. So here we have W upside, and here we have W L by 2. And we have applied the load W here, and we should take V and M. And so V should be taken upside, and we should take M anti-clockwise, and this is the moment about this point. Okay, so we have taken all the forces. So here I am strictly taking second cut. This should be there, but there is no requirement of first cut, because at the end we are applying equilibrium condition, and at the end I want to get the value of V and M. These two values of V and M here. I don't require these two values of V and M. Instead of dealing with these V and M, I can take till the left end so that known values are there, or constant values are there. So instead of applying equilibrium condition for this and getting the value of V and M, you can easily apply equilibrium condition for this and get the value of V and M. Everybody understood what we are doing? Every time I will not be drawing this step. Directly we will write down the range with respect to this diagram only, but we will put this diagram itself. Understood? So if you do the calculation, you will get V plus W minus W is equal to 0. So V will come out to be 0, and M anti-clockwise, W into, if you do it, you will get the value of M also equal to 0. Kindly check it. M anti-clockwise, W into X clockwise, W into L minus L by 2 minus X clockwise, W L by 2 anti-clockwise, all should add up to 0. Everybody understood? Everybody understood? What I did was, instead of dealing with this diagram, which is from here to here, I took the whole left part of the second cut here. Instead of taking till here only, I am taking the whole thing. But whatever, whether I take this one or this thing, second cut is included, because at the end my objective is to get the value of shear force and bending moment at the second cut. This is the way you should be dealing whenever there are these multiple cuts. Okay, so whenever you are taking intermediate range of the beam, that will always give rise to confusion. Okay, or that can increase your calculation time. So you should be always having the inclination of reducing your efforts. Okay, so you, instead of taking from here to here, I will be taking from here to here. That's it. I hope it is clear. You guys can you can check M should come out to be 0, because I remember it. You can check the calculation. I am drawing the shear force and bending moment values. So shear force M, X, 0, L by 2 and L. So once copying is over, please let me know. I will explain you how to draw the shear force diagram, bending moment diagram. So this is the last thing you learn in these conventional methods. So remaining two examples, 5th and 6th are simple only, because whatever you learnt in these first 4 examples, you can apply them directly. That's it, nothing more than that. Understood? Now look here. We have to plot these functions. First of all, I am plotting shear force. Shear force is valid, this shear force equation function is valid from 0 to L by 2, where L by 2 is not included. And this is valid from L by 2 to L. Okay, so here this is valid for L by 2 as well. So this is valid for L as well, because though it is not included, if you take the right part of the second cut, it will be including L. Is it right? If you take the right part of the, this value of diagram, right part of the second cut diagram here, so you'll be having shear force V, which is same as this one, whatever you are getting. This one, whatever you are getting. So this will be valid for X is equal to L as well. So we don't need to do that extra step. I hope it is very much intuitive from the diagram itself. So let's plot the diagram here. So from 0 to L, it is equal to minus W. So it is equal to minus W, straight line like this. But X is equal to L by 2 is not included. So I am putting open circle, because L by 2 is not included. From X is L by 2 to L, it is equal to 0. So the function is having discontinuity. So the value of shear force at X is equal to L by 2 is equal to 0. At X is equal to L, it goes on to become 0 itself. So it is horizontal line like this. Understand? And in the same way, if you draw the bending moment diagram from 0 to L by 2, it is according to this one. X power 1, straight line. So straight line means we need 2 points. At X is equal to 0, it is equal to minus W L by 2. X is equal to L by 2, it is equal to 0. The line is like this. Understand? And here we should put open circle, because it is not including L by 2. Okay, it is valid till just before L by 2. Now from L by 2 to L, it is the function M is equal to 0. So here it is maintaining the continuity. Understood? So bending moment value is equal to 0 there. Okay, so if you take V max magnitude, it will be equal to W, and if you take M max magnitude, it will be equal to WL by 2. Any doubt regarding plotting of the diagram? I just used the basic concept of plotting functions. So whatever the range in which it is valid, there only we should plot that particular function. Otherwise it is wrong. So I hope it is clear. Any doubt is there, can ask me. Kindly feel free. I'm just putting the diagram of the next loading condition. Those who are completely clear, you can go ahead with that. Because there's nothing extra to learn in those remaining two examples. So next two are regarding simply supported beam. So fourth one. So it is simply supported beam with point load in the middle. So for this one I will not disturb you. As you guys know the concepts, I want you people to do all the steps on your own. I'll give you some time and later I will give you the explanation and solution on the board. Simply supported beam experiencing point load W in the middle. So I hope there is no confusion. So once you are done copying this previous one, you can take the fourth one and go ahead with drawing shear force diagram, bending moment diagram. If you are able to correctly draw shear force diagram, bending moment diagram for this example means you understood completely. So you got the complete knowledge of this chapter without any doubt. So here also we should take two cuts. So now I'm coming to the crucial step. I should take the right part of the first cut to left part of the second cut, for which the range is including L by 2, not including L. So to make it simple, instead of taking from here to here, I'm taking from starting to here. Distance is x, L by 2. So V plus W by 2 minus W is equal to 0. So V comes out to be opposite of this, W minus W by 2, W by 2 here. M comes out to be M minus W x by 2 plus W into x minus L by 2 is equal to 0. So M plus W x by 2 minus W L by 2, M comes out to be W by 2 into L minus x. So I'm plotting the diagrams. Shear force diagram V, 0, L by 2, L. So it's coming out to be constant. From 0 to L by 2 it is minus W by 2. It goes on like this, but it's not including L by 2, so open interval or open circle. From L by 2 to L it is suddenly W by 2, so there will be jump in the function. So discontinuity is there. This is W by 2. It goes on like this. So here whatever you get at just before L, same value you'll be getting at L also. So you'll be getting like this. Now if you take for bending moment, this is L. From 0 to L by 2 it is Wx by 2, straight line. So x is equal to L by 2, you'll get it as WL by 4. And from L by 2 to L, you'll get like this. So you'll get V max magnitude as W by 2. M max magnitude come out to be WL by 4. It's better if you can remember this, because we had questions in gates based upon this. You can derive on the spot also, but if you can remember, it's good. M max magnitude for a simply supported beam having point load in the middle is WL by 4. Done? Once you guys are done copying, please let me know. We'll go ahead with the next one. Next one is still simpler. There is only single cut. So next one is simply supported beam with uniformly distributed load. Once you're done copying, please let me know. We'll go ahead with the last one. So everybody done copying? Shall I rub the board? So for this, if you apply the condition, equilibrium condition, will get the support forces as QL by 2 on both left and right sides. So for this, you just have to take one cut. I'm taking the cut at x from left side direction. So this distance is x, QL by 2. Q is acting. So shear force V is there, M is there, which is acting about this point. So Q is acting over a distance of x. So for shear force, for bending moment, we'll apply sigma mz0, m anti-clockwise, qlx by 2 clockwise, q square by 2 anti-clockwise. So this gives you, it's anti-clockwise, minus qx square by 2, m minus qlx by 2 plus qx square by 2 gives you the value of bending moment. If you plot them, so this is the shear force diagram equation. X is equal to 0, it is minus QL by 2. X is equal to L by 2, 0. X is equal to L, it is QL by 2. And for bending moment, X is equal to 0, it is equal to 0. X is equal to L also 0. You'll get the maximum value at L by 2, and it is given by QL square by 8. And this is very, very, very important. Maximum value. Okay, so because sometimes it will take some time. So maximum value bending moment, please remember. So whatever the 6 loading case we have seen, if you remember, if you don't remember anything, it's okay. But please remember this thing, because I've seen many of the numericals which is based upon this value, QL square by 8. So Vmax is QL by 2. Max is QL square by 8. If you are done copying, we'll see shortcuts. I'm hoping that shortcuts will blow your mind. Okay, so really at least 1-2 shortcuts are in that way. That means blow your mind means they can help you a lot. So you can, that means whatever, like if you take, that means you can simply do the first step and you can give the answer. At least for the first shortcut is concerned. Anyways, I will explain that and see those respective shortcuts. Once you're done copying, please let me know.